should we talk about it a little more? Were there any exam questions you're like, I'd really like to know exactly how this one should work? Go ahead. Okay. Say more. I don't know what was on your exam, so you will have to remember the question in some detail.
Like x equals 0, and then I have to estimate sine 1 with boundary.
Okay. I think so. I'm assuming it said something like use a Taylor polynomial centered at 0 to estimate sine of 1. Were we given any sort of... Say one more time? Oh, so like we're supposed to use like the third. So use the third degree or the first three terms? Okay. So use the telling so use like so that like the first three terms of a Taylor polynomial centered x equals 0 to estimate sine of 1. Okay, that's not too terrible. So here's what I would have thought of. I don't love the formula for sine of x, but I do remember it. But honestly, I would say, great, I know that sine of x is equal to x minus x cubed over 3 factorial plus x to the fifth over 5 factorial, et cetera, et cetera, et cetera. So if we're asked to use, oh, I should turn off some lights here. So let's see here. All right, I am finding your conversation very distracting. If you could quiet that, thank you. So if we're trying to use the first two terms of this Taylor series centered at 0 to estimate sine of 1, we're just going to use these first three terms and say that sine of 1 is approximately 1 minus 1 over 3 factorial plus 1 over 5 factorial. And at least if that's how the question was asked, that's really all we have to do. You could simplify that more if you felt like you needed to. So you could go one step further and say that's 1 minus 1 over 6 plus 1 over 120, and then get a common denominator and say it's 120 over 120 minus 20 over 120 plus 1 over 120 to get what, 101, right? Yeah, 101 over 120. That's about as far as you can go, assuming we are remembering all the parts of the question correctly. Now, I'll point out, just to kind of to point out a slight difference. If it said use a third degree Taylor polynomial, we'd only want the first two terms, right? Because a third degree Taylor polynomial would stop at x to the third being the highest power. So on the other hand, if it said third degree Taylor polynomial to do such a thing, then we would say that our sine of 1 was approximately 1 minus 1 over 6, which is 5 over 6. Yeah. Uh-huh. I would. Yes. So you can't, so if they're asking you for a specific degree, you cannot go to a higher power. You have to stop at a lesser or equal to power than that degree. Otherwise, you've gone too far. Okay, that seems, assuming we've remembered it correctly, not like a terrible question to be asked on an exam. Other things you might be interested in talking about, other questions from your exam that felt like you might want to explore them. Before I start talking about 3D graphing, which is super fun. Interesting. I like, well, I should say, looking at things is super fun. Interesting. The actual graphing part is kind of terrible because you have to be able to draw pictures to some degree of efficacy that is hard to attain sometimes. I feel like there's something else I want to say here. No, I guess not. So an excellent follow-up question to whichever way this was phrased would have been, can you bound the error? And the answer should be a resounding yes. We can have, for this estimate here, we can say that our remainder is going to be less than or equal to the next term in absolute value. So for this one here, our remainder would have been less than or equal to the absolute value of -1 over 7 factorial, or just 1 over 7 factorial. If that was how we were asked to do it. Here, our remainder would have been, or our error would have been less than or equal to the next term, which would have been 1 over 5 factorial, or 1 over 120. And we get to say that because these series are both alternating series. So your error or your remainder is always bounded by the first term of that alternating series in absolute value. Yeah.
Question, that I took today. There was a question about the sum of an alternating series.
Mhm.
It had to be within a certain error,
Okay.
and it said it didn't have to be the smallest
Okay.
possible one. But it said no less than 0.01.
Okay.
So one.
So can you tell me more about, can you tell me like what the series was, or what the function we were trying to estimate was?
It was, of course, -1 to the n over. Was it a geometric or? Oh yeah, n cubed.
-1 to the n over n cubed plus 10?
Yeah.
And I assume we're summing this from n equal to,
It was 2 to infinity.
okay. And we were asked to estimate this sum? Or-
no, sorry, 2 to n, and then you're supposed to find n that approximates it within 1/100,
So we want to find,
no greater than 1/100.
and so that the above partial sum estimates the infinite sum.
Yes.
Well, you might be in luck. No, I mean, because I might not know how to answer it. So that this estimates to within, what was the 0.01? Okay. Okay. So it's alternating, right?
Yeah.
All right. So basically, I'm going to write out some number. So basically, I'm going to say we have, so the sum from n equals 2 to capital N, -1 to the nth, over n cubed plus 10. It's going to look like 1 over 2 cubed plus 10. So that looks terrible. -1 over 3 cubed plus 10, plus 1 over 4 cubed plus 10, all the way to, our -1 to the capital N over capital N cubed plus 10. And then the next term, -1 to the n plus 1 over n plus 1 cubed plus 10, plus the rest, right? So again, I should say, this is what we're actually using, right? This is our estimate. And here's the remainder that we're off by. Right? This is this infinite sum out to the right here is exactly what we're missing. And so I guess I should have written it like this. Apologies. There's your infinite sum, right? And I've got my first capital N terms and then the n plus 1 terms after that. And we know that since it's alternating, right, which is always what we hope for because it's so much easier when it's alternating, that the remainder is bounded by the first term of this remainder series. So we know that our error is less than or equal to the absolute value of -1 to the n plus 1 over n plus 1 cubed plus 10. And then we want that to be less than or equal to 1 over 100. This is how I'm imagining doing it. So then I'm going to say this is 1 over n plus 1 cubed plus 10 less than or equal to 1 over 100. I'm going to cross multiply. I'm going to have 100 less than or equal to n plus 1 cubed plus 10, subtract 10. 90 is less than or equal to n plus 1 cubed. And at this point, I would probably just try to guess a number. Right? I don't find any value in like multiplying this out, trying to solve for it. Like, I'm just gonna say, well, let's see. 2 cubed is 8, 4 cubed is 64, 5 cubed is 125. So 5 is gonna do it. So I need n plus 1 to equal 5. So I think I need n to equal 4. But a bigger number also would have been sufficient, depending on how it's phrased. Yeah.
But like,
So here's the thing though. So n has to be an integer. So you could so I right, I'm rounding up here. So what I could have said is I'm saying that right, n has to be bigger than the cube root of 90 minus 1. Right? Yeah, cube root, right? And then the cube root of 90 is between 4 and 5. So I have a number between 4 and 5 minus 1, so a number between 3 and 4. But then I can't say the number's like 3.27, right? Because I can't add up 3.27 pieces, right? I have to add an integer number. So I would round up to the next positive integer and say 4. I would still say it's worth, I mean, as far as I'm concerned, not being the person who's grading your work, saying that n has to be bigger than this still shows you know what you're doing. I don't know if they need you to jump to that and say, well, yeah, that means n can be 4 or bigger.
That you think, but that will be a point.
I would imagine well, again, I can't speak for your instructor, right? Or the TA that's grading it. I would imagine if they're writing a rubric, usually they're trying to give students partial credit because right, we're trying to award points for having knowledge about what's going on. So I would imagine getting to this is certainly worth something, maybe everything, but again, I don't know actually. How helpful. What other things would you like to hear about? Yeah. No. Okay. All right. Well, let's then move along to the next portion of the class. So we're going to completely change directions. So if you really haven't been a fan of this serious stuff, good news, we're not really going to use it anymore. Let me double check that in my mind. Yeah, because we do all, yeah, right. You know, we're kind of done. Now that doesn't, so I'll remind you, many of you probably have a cumulative final, which means the serious stuff, although it's not going to show up for the next, 6 weeks? It's still maybe on your, you should probably ask your professor, is this serious stuff going to show up on our final? Can I completely forget about it? Now, you probably shouldn't completely forget about it because it's not something that's going to go away. Like it is a thing that gets used in future things for various purposes, but you can probably stop thinking about it for a little while. Anyway, well, let's move along to graphing in 3 dimensions. And what I'll probably say a lot of is there's a lot of analogs to 2-dimensional graphing. So let's actually kind of start with a few things here. So let's just plot a point. We're going to plot the point 2, 4, 6. And just like in the XY plane or the 2-dimensional coordinate plane, X comes before Y. In the 3-dimensional coordinate plane, X comes before Y, comes before Z. There's a pretty standard way of drawing the XYZ coordinate plane is not the right word, coordinate space, the XYZ space. So usually we draw it like this, where the x-axis is pointing towards you, the y-axis is pointing to your right, and the z-axis is pointing up. A lot of the time in the room, I will refer to, no, it's terrible, that corner is not a very good corner over there, but I can refer to that left corner there, like the bottom corner that we can't really see, this room is extra terrible, as the origin. That's your 0, 0, 0 way over there, and then this line along the wall right here on the floor, that is your y-axis. That line on the wall over there is your x-axis, and that line pointing up towards the speaker, where those two walls meet, is your z-axis. So again, the x is pointing towards us. The positive y-axis points to the right, the positive z-axis points down. And then that's only 1/8 of all space, right? Over there on the other side of that wall is where y is negative. Down below us is where z is negative. Behind that wall is where x is negative. I find that to be a helpful way to think about this. So we are living in the first octant, the octant where everything is positive. Just like the first quadrant is the quadrant where x and y are both positive. Unlike the quadrants, the other octants don't have numbers. So like in 2 dimensions, right over here in 2 dimensions, where this is x and this is y, you have quadrant 1, quadrant 2, quadrant 3, quadrant 4. No such thing in the XYZ space. You have quadrant 1, sorry, you have octant 1 where everything is positive, and then other octants where we don't number them. Because there's not really like a good way of deciding which way. You can't like go counterclockwise and like it's like there's no like direction to travel to get through everything kind of nicely. So here's your first octant where x is positive, y is positive, z is positive. I'm always going to refer to the ground or the floor as the xy plane. So if I want to plot this point, I need to go 2 in the x direction, 4 in the y direction, and 6 in the z direction. Which is kind of terrible. And plotting points in 3 dimensions is to be honest, kind of awful. But we can do it. It just requires a lot more work than the 2 dimensions. So I need to go. So we're going to try and draw like a whole kind of parallel pipette or 3-dimensional rectangle. I'm going to go 4 in the y and 6 in the z. So if I go 6 in the z first to the point 0, 0, 6, that looks really small. Let's zoom in a bit. There's 0, 0, 6, or here's the point over here, 0, 4, 0. From here, I'm going to go over that way, or from here, I'm going to go up that way. And right there is the point 0, 4, 6. Essentially finding where the parallel lines cross each other. Or in this direction, going 2 in the x direction is going to get me to the point 2, 0, 0. And then from there, I'm going to travel parallel to the y-axis. Or from the y-axis, I'm going to travel parallel to the x-axis, which is always a problem. Not a problem, just more challenging to travel parallel to the one that's not like perpendicular to the other two. So there's my point 2, 4, 0. And then finally, I can travel up from the x-coordinate parallel to the z-axis, or from the z-coordinate parallel to the x-axis, and get the point 2, 0, 6. And then finally, after finding all the points I didn't want, I can travel from this coordinate parallel to the y-axis, from this coordinate parallel to the z-axis, or from this coordinate parallel to the x-axis, and end up at 2, 4, 6. Right there. So it's kind of often described as if you're trying to find a point in 3-dimensional space, it's the point that is on the corner that is opposite the origin of a box that has those dimensions, where x is 2, the x length is 2, the y length is 4, and the z length is 6. But nobody's really asking you to plot points in 3 dimensions, but it's the thing we should be able to think about doing. But really, you could just, right, if you didn't draw this little box here and someone just drew a point right there, it's really hard to kind of tell where it's actually supposed to live because, right, we're trying to plot a 3-dimensional thing on a 2-dimensional piece of paper. So we're limited by our perspective and our drawing abilities. Okay. Let's see what else. Make sure I'm saying all the things. So let's talk about some planes here. Yeah. Let's use black. Where's my black pen? Cool. Let's talk about the coordinate planes, which come up a lot. I should zoom back out. There we go. Let's make sure we keep things on frame. Let's zoom. Sorry, that's terrible. Okay. So coordinate planes. Coordinate plane. Ooh, that's really not straight. Coordinate planes are kind of like coordinate axes in 2 dimensions. Kind of. They're kind of analogous, meaning, so to find, say, like the XY plane, in fact, let's just draw it. So if I was asking you the, oh, geez, my picture be on camera. Okay, here we go. If I was asking you for the equation of the x-axis it has an equation. It's kind of boring. It's y equals 0. In the same sort of way, the equation for the xy plane, well, you want everything on the floor, z is 0. You haven't moved above the floor or below the floor. So the xy plane is just z equal to 0. And I've probably written it in the place I didn't mean to write it. I'm going to draw it down here, or I'm going to draw part of it. Here's my xy plane. And in a similar way, here's my YZ plane. Where, not surprisingly, x is equal to 0. And over here, there's my XZ plane, where y is equal to 0. Or the walls in the room, the wall behind me is the YZ plane, the floor is the XY plane, the wall to your left is our XZ plane. There are lots of planes we can talk about. Some of them are easier to describe, some of them are harder to describe. For example, if I go back to that picture I'd drawn before, I feel like this is not great here. Let me draw this next part a little bit better here. So I'm just drawing the positive parts of the axes for a second, because sometimes that's a nicer way to draw things. So if I look back at that point, let's go a little bit further here. Yeah. You kind of do that longer than I meant to. Oh, well. So if I go back to the point I'd drawn before, oh, so much drawing. So let's do that. Over there. So watch how I'm doing this, right? To find the point, sorry, the point at 2, 4, 6 again, I'm going 2 in the x direction, 4 in the y direction, and then I'm kind of just finding all of those intersections. And there is a reason to draw this, not just because I want the picture again. So here's our nice little box. There's your point 2, 4, 6. Up here, you could say that this plane up here, well, that plane, everything is a height of 6. So here we have a plane that is z equal to 6 in red. And I'll say this again, I'll try and say it every time, right? I'm only drawing a portion of the plane. Just like you only draw a portion of anything that's infinite because, right, it's infinite. And then out here in front, right here, we have the plane x equal to 2. Because every point on this plane has an x coordinate of 2, and the y and z coordinates can kind of be whatever. Wow, that looks not great. And then over here on the right, we have the plane y equal to 4. Because every point on that plane has a y value of 4, and x and z can be anything. So x equal to a number, y equal to a number, z equal to a number is going to give you a plane. And more specifically, I should point out, this z equals 6 plane is not surprisingly parallel to the xy plane, where z is equal to 0. And this x equals 2 plane is parallel to the yz plane, where x is equal to 0. And this y equals 4 plane is parallel to the xz plane, where y is equal to 0. Yeah, cool. Let's look at some other things we should have awareness of. What time is it? Okay, we got time. We got time. So let's try to stay on the screen. Oh, that's interesting. That piece of paper should not be there. So looking at some other things. So in 2 dimensions, this equation, x minus 3 squared plus y minus 1 squared equal to 25, would be an equation of a circle. With a center of 3, 1, and a radius of the square root of 25. Yes. Good question. Yeah. Yeah. Let's look at the syllabus. Can we? Yeah, you look at the syllabus. Let's see. Math. Let's take a look and see. Because I don't remember exactly what we're responsible for here. I know there's like basically they want you to have like some ability to graph stuff, but like we kind of get more into the that's not what I meant to do. You know what? I'm dumb. I have the syllabus printed out right here. But here's the syllabus in case you're curious where it is, right? Syllabus, and then you scroll down and you undergraduate. Co-21C. Let's see what they say. Let's see, what does it say here? Three-dimensional coordinate systems. How vague. So basically, they wants to have some familiarity with the three-dimensional coordinate system, but I don't think it needs to be, oh, geez, that's interesting. That's not what I want to do. I don't think it'd have to be too rigorous here. So I'm trying to kind of give you an overview of things I think you will need to know, but not like get too into it. Like we're probably not going to talk about all the graphing of my hyperboloids of one sheet and two sheets and that kind of stuff. Like I feel like that's not really what we need to do here. But we definitely need to talk about planes because like it's more kind of like the linear things, which I know sounds kind of weird, but like planes are important, lines are important, things we can describe with vectors relatively easily. So that's kind of the direction we're going, and I know that's not super specific. All right, let's look at the three-dimensional analog. In 3 dimensions, we have something like x minus 3 squared plus y minus 1 squared plus z plus 2 squared equal to 25. This would be a sphere. I can spell sphere. Of a sphere with a center, same idea, 3 comma 1 comma negative 2. Radius is still the square root of 25, which is 5. One moment. All right. Or more easily, if someone said my equation was x squared plus y squared plus z squared equal to 16, that's a sphere. Center is 0, 0, 0. The radius is 4. The question becomes how to describe things. And that's what we're kind of moving towards with using vectors eventually, because we're going to start talking about vector valued functions, meaning functions that have, or vectors that have functions in kind of each of the 1, 2, or 1, 2, and 3 coordinate positions, which can be funky at first. We'll get there, but not quite yet. So let's talk about a few other things. Let's give some geometric descriptions of the following equations. So give a geometric description for the set of points that satisfy the given conditions. Conditions. For example, something like the equations or conditions x equal to 2 and y equal to 3. We don't have a lot of freedom here. In fact, we have 1 degree of freedom because z can be anything, but x has to be 2 and y has to be 3. If we draw that, what's happening here, yeah, fine, is we're going to have all the points where those two surfaces intersect. So Here's the plane x equal to 2, or at least part of it. And here's the plane y equal to 3. Maybe my scale might be a little bit off here. 1, 2, 3. And so this line these planes, x equal to 2 and y equal to 3, intersect in a line. And it's kind of not very interesting. Here's how we're eventually going to describe it as a vector. So you can describe this line as the vector r of t. We usually use r for position, where x has to be 2, y has to be 3, and z can be anything. I'm getting a little ahead of myself here, but I don't think that's terrible. Lines can be described as vectors because just like in 2 dimensions, how all you really need to describe a line is a point and a direction, slope. The same thing is true in 3 dimensions, except slope is less of a good idea because like it matters kind of which way you're pointing to talk about slope. So instead we say a point in a direction. So here, this vector fully describes any point you're starting at, and then you're just moving in the z direction. Again, there's more to say there, but we'll come back to that. Yeah. Also, this would be a great, so just so everyone can see, it's not that exciting if you draw it on Desmos either, but you can kind of see on Desmos how things are going to look here. If you look at, can I do something? Anything? Maybe, there we go. If I look at the plane x equal to 2, which I'm going to extend to 3D, maybe, there we go. And the plane y equal to 3, you can see, oh yeah, they're exactly intersecting in that line. How do you draw that line? Good question. How do I draw that line? I think by doing this. You draw, I have to think about it. I think we're gonna do this. 2, 3, t, and then you let t be kind of anything you want. Did I do it for me? I don't know if I can, do I see it or not? Is it there? Oh, yep, there it is. There's my line. So drawing lines in 3-dimensional space on Desmos, you really kind of have to know how to draw it as a vector because there's not really a better way to draw it or write it. Neat. Let's look at some other things. Oh yeah, let's look at this. What if I wanted to describe x squared plus y squared equal to 4? So in 2 dimensions, what kind of curve would that be or shape would that be? Circle. But we're talking 3 dimensions. So here's the deal. You get a circle, but then z can be anything. So what we actually get is we get a cylinder. So if I draw this, I have a cylinder of radius 2. So I'm going to go 2 in the y direction. And I'm not really going to go 2 in the x direction. I'm just going to make a decent drawing. I'm trying to draw this circle in the xy plane, meaning it has to get tilted a bit. So I'm kind of going to do this. There's my circle that's lying on the ground. And then we're going to prop it up in the z direction. So we're going to go up and we're going to go down. And then we're going to go around. So there's my cylinder of radius 2. Z can be anything, but x and y have to satisfy the equation x squared plus y squared equals 4. That's the front part. That's the back part. Question?
how it works, but it's never like, I don't know, this makes sense, like the Z plane, but wouldn't if you were doing like from the X and Y plane as well.
So one more time.
Yeah.
Like in a different direction? Yeah, probably. So it's right, exactly. Like if I said instead the equation, for example, sure, x squared plus z squared equal to 9. Well, that's also a cylinder, but now instead of opening along the z-axis, it's opening along the y-axis because y is the variable that's not showing up. So we're getting a circle. Now we're getting a circle in the xz plane, which I find harder to draw. So in the xz plane, I'm going to go up 3, go down 3. I'm going to try and draw it so it looks like it's supposed to. And then we're going to go to the right and to the left. And really, you can just go to the right. So like if I go to the right, that's the way my cylinder is going to look. So cylinder of radius 3. Now, if I said take the cylinder and also intersect it with a plane, then we're just going to get a circle. So if instead I said x squared plus z squared equal to 9 and say y equal to 4, then I'm just going to get that same cylinder, but over here at y equal to 4, in fact, let's just do it in red up here instead of doing it down here. So if I said I wanted to graph x squared plus y squared equal, sorry, x squared plus z squared, x squared plus z squared equal to 9, and y equal to 4, that would give me the intersection of those two surfaces. It's where the cylinder, which is all the points around, and this plane at y equal 4 touch each other. So it's going to be exactly, if we go over 1, 2, 3, 4, it's going to be that part of your cylinder. So it's just that circle. Oops, sorry, I can't quite see that. Keep going off screen, sorry. So this circle is exactly the circle where x squared plus z squared is equal to 9 and y is always 4. As again point out, you can totally see the graph of this on a nice graphing tool. I know I've said this before probably, but I'll say it again. I'm very jealous. You guys have these really cool 3D graphing tools that were not things that existed when I had to graph things like this. And so I would feel really terrible if you didn't take advantage of them because you're missing out. So take advantage of them. They're really, I mean, they work. And you can see lots of neat things that were hard to see back when they didn't exist. So there's an x squared plus z. Oh, let me rotate this so it's the usual way. So I would say this is not oriented the way I usually graph my things, right? This has the positive x-axis pointing that way. That seems, and the positive y-axis pointing back. I more am drawing things more like this. I'm thinking of the x-axis coming towards you and the y-axis to the right, which bears discussion. But then if we look at the plane y equal to 4, we can see, can we see? Where those two things, oh yeah, they intersect exactly in a circle where the blue and the gray exactly overlap. Right, because y equal to 4 is a plane. So the thing is, I'm not actually getting the graph of the thing I want. I'm getting the two surfaces and seeing where they cross or intersect each other. That's the thing I want. I think, let me try. Let me turn this off for a second. If we, sometimes you can do something like this. Sometimes that works, sometimes it doesn't. I know there's like maybe a or you just don't need an and sign. Look at that. There's our circle, exactly like we were describing it, right? Kind of cool. Ooh, yeah, all right. Anyway, something else I was going to say was that when you draw your XYZ coordinate plane, it should obey what you might have learned in physics or will learn in physics, which is the right hand rule. So if you use your right hand and you put your fingers in the direction of the positive x-axis and curl them in the direction of the positive y-axis, your thumb should point in the direction of the positive z-axis. It's also the way you figure out the direction of a cross product, which we haven't talked about yet. But if you take one vector, cross it with another vector, and then your thumb should point in the direction of the resulting vector. I'm getting ahead of ourselves, but that's two places where the right-hand rule occurs. But when you're drawing your x, y, z, it's typically x this way, y that way, z that way. Although you could rotate it any way around as long as they're still in the same orientation. But what I really want to caution you against is x coming out towards you, y shouldn't be to the left. Positive y can't go that way, it has to go that way. Okay. I know what I want to say. So let's graph something else. Let's graph, say, z equal to y squared. All right. What variable am I missing? So that means this graph is going to be whatever the normal shape is, extended in the x direction. Just like our two cylinders so far have been circles in one plane, extended in the direction of the missing variable. So here, we're going to get our parabola, z equal to y squared, which is always kind of the nicest axis to draw things on is the yz plane because it's the one that's like on the piece of paper. So I'm going to take my usual looking parabola, and then we're going to extend it in the x direction. Meaning this whole thing is going to come down this way. So this is going to come down like that. This is going to go like that. It's going to go like that. So it's going to look like kind of like that. It kind of looks like this. Look at me. Kind of looks like this, right? It's just your parabola, but extended in the x direction. And what do we call this? We call it a cylinder. How terrible. But typically, things that are like a two-dimensional curve that just get extended in the third direction, they're called cylinders, even if the original shape isn't a circle. More specifically, this is a parabolic cylinder. So don't get confused when someone calls something a cylinder that looks nothing like a cylinder. That's the name we give it. Let's see before I get going any further here. Yeah, that seems fine. Okay, let's actually call it a day a few minutes earlier because on Mondays I have a meeting at 4, sometime after 4 that I'm always late to, and I should try to be not late to it. So we'll call it a little bit early today. We'll continue talking about all this on Wednesday. I think there was something else I wanted to say as well, but I don't. So say it again. Play with Desmos 3D. I think it's kind of fun, like just to graph things and see how it works. It's not a waste of time. I think you'd be well served by